Today, we're tackling a chessboard challenge. Given a standard 8x8 board with a white rook, white bishops, and black pawns, your task is to figure out how many black pawns the rook can capture. It's a test of precise movement and stopping conditions. The problem asks us to count the number of black pawns a white rook can capture. The input is an 8x8 character matrix representing the board. A rook moves horizontally or vertically, capturing the first black pawn it encounters in any of the four directions. It stops if it hits an empty square, another friendly piece, a white bishop, or a pawn it captures. We need to return the total count of capturable pawns. A naive approach might involve iterating through the entire 8x8 board to find the rook. Once found, for each of the four cardinal directions, we could launch a separate traversal. Each traversal would start from the rook's position and continue until it hits a board edge, a blocking piece, or a pawn. This works, but it's not the most streamlined. While the board size is fixed and small, making it effectively constant time, conceptually, we're performing redundant checks if we rescan the board to find the rook on every iteration. The time complexity is big O of 1, constant time due to fixed board size, and space complexity is big O of 1, constant time. The key insight here is that the board is small and fixed at 8x8. We can directly simulate the rook's movement. First, locate the rook by iterating through the board. Once its row and column are found, we'll iterate outwards in each of the four cardinal directions, up, down, left, and right. For each direction, we start from the rook's adjacent square and move one step at a time. If we encounter a black pawn, we increment our capture count and stop searching in that specific direction. If we encounter a white bishop, we stop searching in that direction without incrementing the count. If we hit an empty square, we continue moving in that direction. This process is repeated for all four directions. This approach directly simulates the game rules, making it efficient given the board constraints. Let's trace this with an example, a rook at the center with 3 pawns in its line of sight. First, we find the rook at, say, row 3, column 3. Now we check upwards, move to row 2, column 3. If it's a pawn, increment captures to 1 and stop. Next, downwards, move to row 4, column 3. If it's a pawn, increment captures to 2 and stop. Then leftwards, move to row 3, column 2. If it's a pawn, increment captures to 3 and stop. Finally, rightwards, move to row 3, column 4. If it's a pawn, we'd increment, but let's assume it's a bishop. We stop there, not incrementing. After checking all four directions, we return the total count of 3. For our example, with a rook at the center and 3 pawns in its line of sight, the final count of capturable pawns is 3. This is correct because the rook can reach each of those pawns directly without any other pieces blocking its path. You'll spot this pattern when you need to traverse a grid or matrix with specific stopping conditions, especially for pieces moving in cardinal or diagonal directions. Another signal is when the board size is fixed and relatively small, allowing for direct simulation without worrying about large end performance implications. The time complexity is big O of 1, constant time because the board size is fixed at 8x8. The space complexity is also big O of 1, constant time as we only use a few variables for tracking. This simulation approach is fundamental for many grid-based problems. Try the Queen's Attack 2 problem next. It uses a similar pattern. Don't forget to like and subscribe for more DSA insights.